On this 2015 to 2025 Ford F150 with the 2.7 EcoBoost, P0141 may point to a problem in the downstream oxygen sensor heater circuit. The truck may run normally, but it can turn the check engine light on and may have emissions monitor trouble. Broadly, think about possible heater circuit wiring, connector condition, power and ground, sensor heater behavior, exhaust area damage, and module command or control. Start with the basic system checks before narrowing in. Do not treat these general checks as a complete P0141 pinpoint test. If the exact P0141 branch is not available after the setup work, pause, recheck the earlier diagnostic path, and avoid guessing. Before you put a meter on anything, look for an obvious concern that matches the customer complaint. Check for related OASIS or TSB information if available. Then look for previous repairs that may have been done incorrectly. Make sure the battery and charging system are healthy and verify battery SOC is greater than 70% before starting diagnostics. Scan all network modules for codes related to the concern. If other codes are present, check what they mean first, and diagnose circuit-related codes before system or performance-type codes. If multiple circuit codes are set, look for a common power or ground path before chasing separate faults. Then inspect the harnesses for damage, chafing, and routing. Check fuses, circuits, and connectors for continuity and correct installation, and make sure components are connected. From there, keep the basic checks moving in order. Inspect vacuum lines and the air intake for leaks, routing problems, or restrictions. Inspect hoses for damage, leaks, blockage, and routing. Check fuel quality for octane, contamination, and winter or summer blend. Inspect the fuel tank, fuel lines, and fuel system for damage, leaks, and routing. Check coolant level and quality with the engine at the correct operating temperature. Check oil level and quality for contamination and maintenance condition. And inspect the exhaust system for damage, restriction, and routing problems. Use Rotunda Flex Probes NUD 105R025F or Terminal Probe Kit 418S035 when connecting test equipment or jumper wires to pins. The goal is to test the circuit without creating terminal damage. Check male to female pin fit with the mating pin and feel for normal separation force. A damaged pin will have very low separation force. If a small pin has to come out of the connector hardshell, pin guide, or retainer to remove extra drag during that check, do that as needed. Replace damaged connectors, pins, or terminals. Do not force probes into connectors. Make a clean test connection without spreading or damaging terminals. Use the scan tool to read PID input values, output states, and diagnostic states. Monitor the data in the data logger when you need a detailed look without unnecessary disassembly. Make sure you understand how the module is supposed to control the circuit, and make sure programmable parameters are set correctly for the function being tested. If another DTC is directing the path, resolve that DTC first through the proper diagnostic routine. Then test both hardwired and networked inputs. Then test outputs. Check whether module software updates apply. If output state control can switch the output on and off normally, that points you back toward analyzing the inputs instead of condemning the module. Unnecessary module replacement usually comes from weak testing, and do not apply power or ground directly to module-switched components with jumper wires. For a power-providing circuit carrying approximately 200 to 1000 milliamps, load the circuit with a 250 to 350 milliamp test light and measure circuit voltage with a DMM while the test light is connected. A voltage reduction during that loaded test points to excessive circuit resistance. If the circuit carries more than 1 ampere, load it with a device that needs similar current, such as a brake light bulb. Wire size can help you choose the test method. 24 gauge, 0.5 millimeter, or smaller is generally used to carry approximately 1000 milliamps, 1 ampere or less, while 20 gauge, 0.8 millimeter, or larger is generally used to carry 1 ampere, 1000 milliamps or more. For higher current circuits, voltage drop is the better test. Measuring voltage with the intended load disconnected may only find an open circuit and can miss excessive resistance. Check ground circuits by measuring voltage drop while the component is operating or trying to operate. Use an ohm meter on ground circuits only with the battery disconnected, because normal voltage with the battery connected can corrupt the reading. For most small 18-gauge and smaller wires, expect less than 2 ohms. For most wiring harness circuits, expect less than 2 ohms of resistance. A standard DMM ohm meter's low resistance resolution, approximately 0.1 ohm, limits its accurate use to circuits carrying less than approximately 5 amperes. Reverse the DMM leads and make sure the resistance reading does not change unless the circuit contains a semiconductor. When checking for a short to ground, disconnect both ends of the circuit and expect greater than 10,000 ohms to ground. When checking for a short to another unpowered circuit, disconnect both circuits and expect greater than 10,000 ohms between them. When checking for unwanted contact with a powered circuit, disconnect both ends, turn on ignition run power, and expect no voltage. Only back probe when the circuit has to be tested under real operating conditions. Use back probes made for that job, and remember that a poor probe contact can look like a circuit fault. For a single point voltage check, where 0 volts is a possible result, disconnect the circuit and test normally instead of back probing. For continuity or open circuit checks with an ohm meter, disconnect and isolate the circuit instead of back probing. When using jumper wires, always use fuse jumpers. The recommended universal testing jumper wire fuse is 5 amperes or less, with larger fuse ratings only when the load requires them. Use flex probes or an equivalent tool to prevent terminal damage, but do not use flex probes to carry high current greater than 5 amperes, such as cooling fan or blower motor current. Follow the test sequence carefully, so a wrong jumper connection does not damage a component or harness. When you find the circuit fault, examine it, repair the root cause, and repair any adjacent wiring that was damaged. Never fix a circuit by simply adding a new parallel wire without understanding why the original circuit failed. For voltage drop testing, connect the voltmeter at the beginning and end of the suspect circuit, with the circuit operating or trying to operate, and power available. Connect the meter lead so polarity follows conventional current flow. A 0-volt voltage drop reading usually means bad meter connections or the component has not been turned on. A small amount of voltage is normal circuit loss. In 12-volt circuits, normal loss is usually less than 0.5 volts, or less than 5% of circuit operating voltage. Greater than 0.5 volts indicates abnormal voltage loss from high resistance in wires or connectors. For voltage in, voltage out testing, put the negative meter lead on ground or the battery negative terminal, operate or attempt to operate the circuit, then measure the power side and ground side of the load. The power side should be within 0.5 volts of battery voltage. The ground side should be greater than 0 volts, but less than 0.5 volts. A 0 volts reading or source voltage can indicate an open circuit. The safe way to approach P0141 is to confirm the concern. Handle any higher priority circuit codes first. Protect the terminals, load test the circuit, and use voltage drop before calling the component bad. If the path stops before a real P0141 decision branch, stop and avoid guessing. For more diagnostic training, visit stepdiagnostics.com.